Alright, hey guys. I promised you a video and I promised it around 9, but it's already 10 minutes till 9. So I don't think you're getting anything till about 9:30. Sorry about that. Of course, you won't know that until 9:30 anyway, so I don't know why I'm mentioning it, but getting a bit of a late start, but I'll try to go quickly. How about that? Alright, so is this thing plugged in? I think it is. Alright, we're good to go. I'm looking at homework from day 2 because I already posted an answer key for the other homework, and I posted an answer key for a lot of the practice problems from the packets and stuff too. So there's 3 things posted. They're posted in an announcement. So if you want to find them, go to announcements and you'll find the 3 answer keys. But I'm going to concentrate on this thing, day 2. There's a second, third, fourth, I don't know what it is, but there's another worksheet that I posted that's completely optional, but it has extra practice, and that came with its own answer key too. That came in an announcement. I'll maybe look at some of those problems too if you'd like. Anyway, looking at number 1. So this is a little bit too easy because you have a graph to look at. So imagine if for a moment, copy, paste. I think that worked. Okay, imagine if for a moment you could not see this graph, right? If you had to just go off the function, could you still do it? I think the answer is yes. And there's plenty of problems coming where you have to do it without a graph anyway, so I'll let you have the graph this time. This is number 1, so we're just kind of trying to ease into it. But looking at this function, looking at its graph, looking at the algebraic rule, I hope you would all say, in response to whatever the first question is about just where are we continuous, then we are certainly continuous on the intervals that go from negative infinity to 1, and also from 1 to infinity. Yes. Okay. B, we can see that we have a discontinuity at 1, and it's a jump discontinuity. So I don't know. I don't like this 3-part thing. I think I'm starting to like part B to just be everything. Name it, classify it, justify it, all in one fell swoop. So we might say, because the limit as x approaches 1 from the left of our function, which is called f of x, now that limit equals 4. And we know that is not equal to negative a half. And negative a half is our limit from the other side. And so there it is. There's my limit justification. So we can say because the limit equals 4, which is not the same as the other limit because it's negative a half, we can say f of x has a jump discontinuity at x equals 1. And then that's it. We've now covered the function's entire domain. We've covered negative infinity to 1, 1 to infinity, and now we've addressed what's going on at 1. So for this problem, that's it. This is all you'd have to do. Next problem. So the next one is another one that's supposed to be pretty easy because, again, I'm giving you the graph. So for this problem, you would just say, where are we continuous? We're continuous on the interval that goes from negative infinity up to 5, and from 5 to infinity. And then here we can say because the limit as x approaches 5 from the left of the function. Now the limit is going to be given by the expression where we can't be 5. It's going to be given by the 1, so it's given by the horizontal line. So our limit is 1. And that is equal to the limit from the other side. So because the limit equals 1, but f of 5 equals 3, which does not equal 1, there is a removable discontinuity. At x equals 5. And there it is. Again, we've got the two intervals on which we are continuous. We're stating that we have a discontinuity at 5. It's removable, and it's removable because the left and right hand limits are equal to each other, but that limit is different from the function value. And that's kind of how these arguments are supposed to go, okay? So yeah, as I write these arguments, I'm writing them in a very sort of mathematical way. We could write this sort of more in words, so maybe the next one I'll try to do it a little more just kind of in words rather than using the math. So here's the next one. So we're going to do 3, so let me just cover up 4. And then we can do 3. First we'll do 4. First we'll do 3. Jeepers. Alright, let's do it. And I'm liking that blue color, so whatever. Alright, notice this time you do not have a graph. I'm not going to ask you to graph on the quiz, but you might want to graph. It certainly helps us to decide what kind of discontinuity we have. So I'll tell you what, I will not graph, since I'm not going to ask you to. But what would I do here? I would look at this and I would say that f of x is certainly continuous on, and it's going to be continuous on this whole interval because 2x minus 10, that's just a line. And lines are continuous on their entire domain. So we're definitely good to go on the entire interval that goes from negative infinity to 2. And this next guy, that's a line again. It's technically a constant function, but that's a horizontal line at 0. So we're definitely continuous all the way from 2 to infinity. So the only place where we might have a discontinuity is right at 2. And so think about it. What would be my limit from the left? Well, that would be given by this expression here, because to the left of 2 is when x is less than 2. So plugging in 2 gives 4, take away 10 is negative 6. So I'm just going to jot that down. The left-hand limit equals 6. That's a fact. Now the right-hand limit would be given by this expression, which is 0. So just kind of writing that down, I don't see a picture, but I can imagine in my mind, from the right I'm getting 0, but from the left I'm getting 6. That's a finite distance between them. That's a jump. Oh, you can't see what I'm writing, sorry. I didn't realize I was this far down. Doesn't matter, but sure, I'll bring it up anyway. This is what I was writing, just that the left-hand limit is 6, the right-hand limit is 0. Because those two limits are different, because there's a finite distance between them, that's a jump discontinuity. So now that I know all that, I can go in and I can write a good answer for part B. So let's actually state the limits. I think I still need to say them using proper mathematical notation. So I'll say the limit as x approaches 2 from the left of our function f of x. Well, the left-hand side comes from here, so I'll show a little work and I'll say it's going to be 2 times 2, take away 10. That's 4 minus 10, that's negative 6. So there's that limit. Now I also know that the limit as x approaches 2 from the right. Well, that's just given by the constant function, so that's 0. Now if you want to maybe not use so much mathematical symbols, give me those limits. This is all you need, and now just say since left-hand limit does not equal right-hand limit, though both exist. And are finite. F of x has a removable discontinuity at x equals 2. But there you go. Again, we're continuous from here to here, then we've got a removable discontinuity here. Just if anybody's curious, what would this graph look like? Well, the 0 part's easy. Starting at 2, we would get a solid dot at 2, and we would run to the right. So there's that graph. And to the left of there, plugging in 2, we already saw, gave us Ooh, why did I write -6? Because it is -6, that's why. Okay, so 1, 2, 3, 4, 5. Oh, it's marked right there. So we would get a big open hole here and a graph of the slope of 2. So left one down 2 and left one down 2. Or you could just say there's the y-intercept of -10. We're clearly getting a point at -10. So we've got this line here. So there's your graph. You don't need it, but if you made it, then it becomes a lot easier to see that at 2 we have a jump discontinuity. But honestly, you should be basing your answer on the algebra of finding the limits, seeing that they both exist, and they're both finite, but they don't equal each other. That's a jump discontinuity. Let's do 4. So 4 is another rational function, and we know that they always have discontinuities when the denominator is 0. So I know right away there's a discontinuity at -1. But if that cancels, then I'll just get a hole, and that'll be a removable discontinuity. If it doesn't cancel, then I'll get a vertical asymptote, and that'll be an infinite discontinuity. So you want to factor the numerator. And the numerator gives an x minus 2 and an x plus 1. That means that that factor of x plus 1 does cancel, giving me just x minus 2 as an equivalent form of this function. And so that tells me that, first of all, this guy's going to be continuous on. Pretty much its entire domain of all real numbers except for the -1. So it'll be continuous on negative infinity to -1 and -1 to infinity. And I know that because this canceled, we're going to get a hole. So in part B, I can say there's a removable discontinuity. At x equals -1. Because. And again, to prove a removable discontinuity using limits, you have to show that the left-hand limit equals the right-hand limit, but does not equal the function. So it would be the limit as we approach -1 from the left. That's going to equal some value. And we can show that that value is the same as the limit as x approaches -1 from the right. And then we can show but f of -1 equals something different. So what's the something different? The something different's easy. If we evaluate the function at -1, you have to evaluate the original function, including the 0 in the denominator. So f of -1 is undefined. But when you evaluate the limit, we're going to use that factor and simplify and substitute method. We can go ahead and just evaluate this simplified expression here. We can just plug -1 into that, and we get a limit of -3. So that justifies the fact that our discontinuity is removable, because the left and right hand limits are equal, but the function is different. By the way, what does this graph look like? Well, it's just a line. It crosses the y-axis at -2. And it has a slope of 1, so it goes up 1 over 1, up 1 over 1, up 1 over 1. Now it goes left 1 and down 1. That's what puts me at -1. There's my hole right there. And then it goes down 1, down 1. But the graph of this function is a line with a hole in it. We know that the x-coordinate of the hole is -1. And you can now see graphically that the y value is -3. But we already knew that anyway from our algebraic approach. But there's your graph. Everything we've said here is true. So there. Okay, that was 4. Here's 5, 6, 7, 8. And then 9, 10, 11, 12, 13, 14. That's a lot. Oh well, I said I'd do them, so I'm going to do them. It is 9 right now. So maybe in a few minutes I'll chop this and post it, and then I'll send you more in a minute. But why don't I do one more problem at least, and then I'll send you guys a part 1. Okay, so this says, without using your calculator, find the intervals on which the following functions are continuous and identify and classify any discontinuities. I think what that means is you didn't have to be doing all this limit stuff for these first few problems. I don't mind that I'm doing it. You could have gotten away with not doing it, I guess, because that's justify. When we get to the next batch, when we get to the 9, 10s, 11s, that's when suddenly that keyword justify shows up. Justify using limits. So I don't need to be doing that, but I'm going to keep on doing it anyway, just to keep giving you guys the practice. So why don't we do 5? Let me duplicate this a few times. Duplicate, duplicate, duplicate. Okay. Boom, 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 boom. All right, so we're doing 5 first. Throw that in the bin. All right, I would like to think that for 5, it's a rational function, just like the one we did before. See this rational function? And we said whenever the denominator was 0, we would get a discontinuity. So looking at this function, ideally you can do the math in your head and see that -2 will make us 0. If you can't, then just literally grab the whole denominator, set it equal to 0, and then solve algebraically. You get 2x equals, subtract 4, so -4. You divide, and there's your -2. This is how I know that -2 is the 0 of the denominator. So -2 is going to be for us a discontinuity. Now what kind is it? Well, it definitely doesn't cancel out this time. Even if I did factor, the x squared is x squared. I could factor a 2 out of the denominator to get x plus 2, but nothing's canceling. So this is definitely going to be an infinite discontinuity. So in part A, again, you can tell me. Now, rational functions are continuous everywhere except for those zeros. So again, we can definitely say that we're continuous on the interval that goes from -infinity up to my discontinuity, and then from my discontinuity to infinity. That seems to be pretty standard for most functions. It's not always true, but it is usually true that you're continuous from -infinity up to whatever discontinuity you have, and then from whatever discontinuity you have to infinity. Now we know f of x has an infinite discontinuity at x equals -2, because the limit as x approaches -2 from the left, that's going to equal something, and I do have to check both sides of the limit. So the limit as x approaches -2 from the right of f of x, that's going to be something. Now if you know much about rational functions, you know that on either side of an asymptote, ours being at -2, there's not a ton of options. And again, actually we have a slant asymptote here, so this is a little trickier. I'm just going to pretend we had a horizontal one anyway, just for a hot second. But think about it. Typically, don't we get a branch that's under and then a branch that's over? So that from one side you get a limit of -infinity, from the other side you get a limit of +infinity. That's one option. Another option is that the first branch is actually above, and then the second branch is below. And then your limits would switch. Your left-hand limit now is +infinity, and your right-hand limit is -infinity. This guy's going to be a little different for us because the numerator is squared. So how do I test and figure out where my branches are? Well, literally just plug in points. Use a numerical approach and just evaluate. We're over here at -2. So imagine plugging in a number just a little bit more negative than -2. Well, in the numerator, -2 squared, or something more than -2, or technically something less, something left of. When I square it, it'll still give me a positive. But downstairs, if I'm less than -2 and you add 2, that'll give me a negative. Times 2 is still negative. So I know that to the left of 2, we are going to be negative? Well, maybe I lied about the squared then. Maybe the squared doesn't matter. Rats. Okay, I'm just going to keep going. To the right of -2. Now imagine if we did the same sort of testing. If I'm to the right of -2, then that number squared is still going to be positive. But now that I'm a little bit bigger than -2, adding 2 will give me a positive, and multiplying by 2 will give me a positive. So I'm now positive over a positive. So on this side, we're positive again. So that's one way you could get at these limits, was just to take that numerical approach and think about the behaviors to the left and right of the asymptote. And if I'm getting a negative number very close to the asymptote, then I know I'm going down. So this limit from the left is going to -infinity. The one from the right, though, is giving positive values, so that guy's going to positive infinity. And that's good enough for me. That's that whole problem done. And again, this graph is not really quite right, because we would have a slant asymptote here. So this graph would look a little different. But as far as coming up with those limits, what we did was fine. Let's do, oh no, I was going to stop now. Yeah, fine, I'll stop now, just to make sure you guys have something to be looking at before it gets too late. But I'll pick up from here again, and I'll send out the rest as soon as they're done. See you tomorrow.